Hi everyone. In this video, we'll go through a few basic examples of balancing equations to demonstrate why we balance chemical equations and how we can balance chemical equations. So in our first practice question, we have an example of a chemical equation. The chemical equation demonstrates that hydrogen gas, which is represented by the symbol H2, and oxygen gas, which is indicated by the symbol O2, react together to form water, and water is represented by the symbol H2O. In the chemical equation, the species which are on the left-hand side are called the reactants, while those that are on the right-hand side of the equation, or on the right-hand side of the arrow, are called the products. If we look at the left-hand side of the equation, which is the reactant side of the equation, we can see that there are two H2 atoms per molecule of H2 gas. And we also have two O atoms for each molecule of O2. Looking at the product side of the equation, we have two H atoms and we have one O atom. This means that if I were to react one molecule of hydrogen, which has two atoms of hydrogen, with one molecule of oxygen, which has two atoms of oxygen, then I would form H2O, which has two atoms of hydrogen and one atom of oxygen, plus I would have one extra atom of oxygen that is remaining. Because balanced chemical reactions are the simplest whole number ratios that chemicals can react with each other to complete a complete reaction without leftover reactant, we would say that this equation is unbalanced. So to balance the equation, we need to determine the appropriate ratio of coefficients that we can add in the blank spaces here in order to make the equation balanced. So to balance the equation, we need to determine the appropriate ratio of coefficients that we can add into these blank spaces to this equation. First, what we should do is we should look at the elements which are exclusive to a single reactant and a single product. So for example, hydrogen, H, is only found in H2 on the reactant side, and H is only found in H2O on the product side. Similarly, oxygen is only found in O2 on the reactant side and found in the H2O on the product side. What this means is that the ratio of water to hydrogen gas must be 1 to 1. And similarly, the ratio of oxygen gas to water must be 1 to 2. That's because we need to have the same number of atoms on both the left-hand side and the right-hand side of the equation. So first I'll start off with the oxygen. Because I need to have 2 times the amount of water in order to have the correct number of oxygens, I would add a 2 in the front of this equation. What that now indicates is that I have a total of 2 oxygens on the product side, as well as 4 hydrogens on the product side. That's because the coefficient multiplies the number of atoms that are indicated in the chemical symbol by that number. So for example, I have 2 hydrogens in the water. Since the coefficient is 2, 2 multiplied by 2 equals to 4, and I have 4 hydrogens. Having no subscript indicates a subscript of 1. There's 1 oxygen per molecule of water, and multiplied by 2 means that there are 2 atoms of oxygen. Now, looking at the left and the right hand side of the equation, the number of oxygens is now said to be balanced if there is only 1 molecule of oxygen gas. Now we can look at hydrogen. There are a total of 4 hydrogen atoms that are remaining on the product side, which must be balanced with the hydrogens that come in pairs on the reactant side. By adding a 2 in front of the H2, there are now 2 H2 molecules, and thus there's a total of 2 multiplied by 2 H atoms, which means that there is now a total of 4 H atoms. So, counting, we have 4 H atoms, 2 oxygen atoms, 2 oxygen atoms on the right hand side, and 4 hydrogen atoms on the right hand side. So by adding the coefficients 2, 1, and 2, we now have a balanced equation which has the same number of atoms on the left and the right hand side of the equation. What we could have done alternatively is we could have decided to start by balancing the hydrogen first. If we had a ratio of 1 to 1, we would now have 2 hydrogens on both the left and the right hand side of the equation. However, there is only one oxygen on the product side as opposed to 2 that is on the reactant side. There is already a coefficient of 1 next to the water on the product side, so 2 cannot be added to balance the remaining oxygens. What can be done is a fraction, half, can be added to the coefficient of O2 on the reactant side. This means that now the number of oxygens is equal to 1, and so the number of hydrogens and oxygens is equal on the reactant side as well as on the product side of the equation. However, we commonly would not leave fractions as coefficients, so what we would do is we would normally multiply everything by 2, meaning now we would have a 2 in the front of H2, a 1 in the front of O2, and a 2 in front of the H2O, which was the same ratio that we had gotten when we started by balancing the oxygen. In this next example, nitrogen gas reacts with hydrogen gas to produce ammonia gas. Again, we look for which elements are exclusive between one reactant and one product. Nitrogen is exclusive only to N2 and NH3. Hydrogen is exclusive only to H2 and NH3 as well. This means that we could choose either one of N or H to balance first. However, the nitrogen is easier to balance since the number of hydrogens in the nitrogen gas and in the ammonia are in a whole number ratio as opposed to the H2 and the H3. So what we can do to balance this is we can add a 1 in front of the N2 and a 2 in front of the NH3. This means that now we have 2 N's on both the reactant and on the product side. The number of hydrogens we have are 2 multiplied by 3, which equals to 6 hydrogens. H2 has 2 hydrogens per molecule, which means that we would need to have a number which multiplies by 2 to equal to 6 as a coefficient. This number is therefore going to be equal to 6 divided by this number, which is 2, which is equal to 3. And so now the number of H's that we have on the reactant side is equal to 6. Now we have the correct number of nitrogens on both sides, as well as the correct number of hydrogens on both sides. Here we have a slightly more difficult example which involves multiple compounds in what we call an ion exchange reaction. When completing the balancing of these types of equations, we will have to consider the polyatomic ion SO4. SO4 is a polyatomic ion known as sulfate, and polyatomic ions often behave as individual units when balancing these types of equations. So that means that SO4 is not going to break down into S and O, and will remain as SO4 after going from the reactant to the product side of the equation. So in balancing the equation, we can start with any atom of choice, but let's go with the polyatomic ion SO4 just to illustrate to you how it behaves. So in this ion exchange reaction, we should expect the SO4 to exist as SO4 on the product side. And that is actually what we also see in the form of calcium sulfate. We can see that the sulfate is exclusive to the potassium sulfate on the reactant side and the calcium sulfate on the product side. Since there is only one sulfate ion in both of these species, we know that they must have a ratio of 1 to 1. Now that the SO4 has been balanced, we need to balance either the calcium or the potassium. If we choose the potassium next, potassium is exclusive to the potassium sulfate and the potassium bromide. That means the ratio of this number to this number must be equal to the K2 to the K, and therefore this number must be equal to 2. So now, looking on the right hand side, we have 1 SO4, as we do on the left hand side. We also have 2 Ks, because it's 1 times 2, and we also have 2 Ks on the right hand side. We now also have 2 Brs, 2 bromines that we need to balance. Bromine is found exclusively in potassium bromide and calcium bromide. Since there are already 2 bromide ions in the calcium bromide, this must be in a ratio of 1 to 2. So a 1 can be added to the coefficient. So the bromines are the same on the product and the reactant side. as are the potassiums and the sulfates. The calciums have a total of 1 atom on both the reactant and on the product side. Since the number of calciums is now also balanced, we can confirm that these are the correct coefficients which will go before the species to leave us with a balanced equation. This next question is very similar. While in the previous question there was a polyatomic ion SO4, in this question there is also a different polyatomic ion which is in the form of hydroxide OH. While it may not be obvious, the hydroxide continues to exist as OH, however combined with H in the form of H2O. Because H2O is simply OH plus an extra H attached to it, making it H2 and O. Since the OH is only found in the lead hydroxide and in the H2O, we can start by balancing these two species. There are two OHs in the lead hydroxide, but equivalently there is only one OH in the H2O. This means that the ratio of lead hydroxide to water must be 1 to 2. So now the number of OHs that we have is equal to 2 on the left hand side, and the number of OHs is equal to 2 on the right hand side. Since there are 2 extra H's on the product side than the reactant side, what we now need to do is balance those 2 extra H's with whatever is left over on the left hand side. So here we still have H's that are in the HCl, and we have a total of 2 extra H's that were not from the OH. So to balance these two equations, we will need to have a 2 in front of the HCl. This means that now the number of H's that we have is equal to 2, and remaining we now have 2 Cl's and also 1 Pb. Well, conveniently we have 1 Pb and 2 Cl's in the form of PbCl2, which means that there should be a coefficient of 1 to balance the remainder of this equation. In this equation there is an incomplete combustion reaction, and because it is an incomplete combustion reaction and there is a longer chain hydrocarbon fuel, C8H18, there can sometimes be multiple answers which are also correct depending on how we decide to balance the CO2 and the CO. For this equation, I would first start by balancing the H2O and the C8H18. This is because these are the only two chemical species for which H belongs to exclusively. We cannot pick C because it belongs to 2 species on the same side. We also cannot pick O because it belongs to 3 species that are on the same side. So in order to make the number of H's equivalent with 18 H's on the left hand side and hopefully 18 H's on the right hand side, we would have to add a number 9 in order to balance these two with a number 1. From here we have 8 C's and O's which we can split between the CO2 and the CO. We should not pick O to balance next because a coefficient can be added in front of the oxygen in order to balance whatever remaining oxygens there are. What we should do is we should pick the C's to balance. As I said previously, there can be multiple correct answers depending on what the ratio of C's we would like to choose. It does not matter what these coefficients are so long as this number plus this number is equal to 8. So let's say I decide to go with the numbers 6 and 2. Well, what I have now is I have a total of 8 C's, which is equivalent to what's on the reactant side, and I will have 12 plus 2 is 14 plus 9 oxygens. 6 times 2 is 12, plus 2 is 14, plus 9 is 23 oxygens. Well, these oxygens can simply be balanced by adding the coefficient 23 on 2 to the left-hand side, and then multiplying everything by 2 to remove the denominator. Let's say now I go with different numbers, 4 and 4. Well, now I have 8 C's on both sides, but the number of oxygens I have are 8 plus 4 is 12 plus 9 equals to 21. Well, then that means the number of oxygens that I would need are 21 on 2. And again, I can multiply all of the coefficients in the equation by 2 to remove the denominator. And just to give you one more example, let's say that I go with 3 and 5. The number of carbons is 8, and the number of oxygens is 6 plus 5 plus 9 equals to 20, meaning that a coefficient of 10 would be required to be added in front of the O2. So as you can see, for this type of equation, multiple different answers can be given depending on the relative number of oxygens that are utilized or the relative number of CO2 and COs that are produced. For our final reaction, we have an acid-carbonate reaction. Hydrochloric acid is reacted with calcium carbonate to form calcium chloride, water, and carbon dioxide. This reaction is a little bit more unique in that the carbonate polyatomic ion CO3 that is in calcium carbonate is separated into carbon dioxide as well as the oxygen that is included in the water. However, the steps required to balance this equation are exactly the same as we have done previously. So in the equation, hydrogen is exclusive only to HCl and H2O. Chlorine is exclusive only to HCl and CaCO2. Carbon is exclusive only to CaCO3 and CO2. We could begin balancing with any combination of species as long as they have elements that are exclusive only to those pairs. So let's try for H. The ratio of HCl and H2O must be 2 to 1 in order to make sure that the H's are now balanced. Remaining, we have two Cl's, which are exclusive only to HCl and CaCO2. This means the ratio of HCl to CaCO2 must be 2 to 1. Next, we can balance the calcium with the calcium carbonate. Since we want to have one calcium atom on the left-hand side, the coefficient must equal to 1. Finally, we need to balance the carbon dioxide. There is already one oxygen from the H2O, which means that we only need to have one carbon and two oxygens remaining on the right-hand side. We can find that extra carbon and oxygen in the form of CO2, meaning we only need to add a 1 in front of the CO2 to have our balanced equation. And this will be our final answer.
Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.